So today I present you the work that I made during my first year of PhD, which is entitled Real-Time Detection of Mercury Traces around nanogram per liter using DNA-based biosensors. And I would like to thank my co-directors, Claudia Cosio and Julien Proust, and also Aurélien Briand for this work, and all the partners, laboratories and so on for the fundings of my PhD. So, as a brief introduction, it exists two kinds of family of emission of mercury. You have natural emission and anthropogenic emission of mercury. For example, in the case of France, you can find cement production, waste from products, ferrous metal. And in the case of India, for example, the main source of emission is stationary combustion of coal. So in the environment, mercury exists into three forms mainly. Elemental form Hg, mercuric ions Hg2+, and methyl mercury ions. And these three forms coexist in the environment into a relatively complex cycle between atmosphere and soils, water, and so on. And you can find, for example, bioaccumulation of methyl mercury in fishes in the food chain. So, yeah, mercury can cause different diseases for humans. So you can have some diseases on your brain, liver, lungs, heart, and so on. And you can have also, as I said, some problem in your alimentation because of bioamplification of mercury in fishes. So with this observation, you understand easily that we need some device to detect mercury traces. Nowadays, the main device that we use is atomic absorption spectrometry, inductively coupled plasma mass spectrometry, and cold vapor atomic fluorescence spectrometry. But so these techniques are very useful and very sensitive to mercury. However, they present three main drawbacks. The first one is that you need to sample a solution, so you lose information depending on where you make the sample, and between two samples you have no information. The second one is the fact that this technique is relatively complex and time-consuming. And the third one is that it's a relatively heavy machine, so you put it in a laboratory and it stays here during a few years. So the idea is to give a response to these drawbacks and use DNA as a detection tool. So why using DNA for detection of mercury? Because in the last decades, some researchers show that there is a particular affinity between thymine, which is one of the four bases of the DNA, and mercury ions. So through this form of this complex, thymine, Hg2+, thymine. So the idea is to use this affinity to capture mercury ions. For this, again, inspired by the literature, we designed a specific DNA strand rich with thymine, and which has the particularity to fold into an hairpin shape in presence of through the formation of this kind of complex thymine, Hg2+, thymine that I presented just before. So now the question is how we can be sensitive to this folding. For this we will use SPR detection. So I will not go into the details, but Aurélien and Mahatma present SPP and so on. So the idea is to use a metal layer and a dielectric layer and functionalize this gold layer at the interface to be sensitive to SPR and pass different concentration of mercury in the dielectric medium and observe the interaction between DNA and mercury. So for this, I use an IPSO lab, so the SPR that you showed during the demonstration of Aurélien 2 days before. And here you have different point of view of this device, with the solutions that you want to test, different tubes for the fluidics, and syringes to withdraw the solution. So here is a prism, and here, for example, some figures of this prism, with our DNA, and the idea is to observe the folding of the DNA by a progressive increase of the concentration of mercury ions. So with this SPR, you can measure two kinds of signals. First one is sensogram, so you fix the interrogation angle and you observe according to the time the evolution of the signal. It allows us to analyze association, dissociation, regeneration of the prism and so on. And the second one is angle scan. So at the resonance, you will have a huge decrease of the intensity of the signal because the free electrons take all of the energy of the incident beam. So this group designs the resonance of the signal, and you observe the shift of this signal, and the shift can be related to the evolution of the refractive index into the channels. And the particularity of this SPR is that you can measure the phase, and so you can be very sensitive to the shift because of the sharper part of the phase signal. So SPR is very useful because it works in real time with a high sensitivity and label-free. And the particularity of this SPR is compact the volume of the device and the fact that you can measure phase. So you can use SPR for drug analysis, vaccine, and biological tests, and so on. So here are the results. So we compare two forms of mercury, methylmercury and mercury cations. In the case of methylmercury, we have a progressive binding of the methylmercury to the thymine, but because of the valency of one of the molecule, you can't induce the folding of your DNA, and so it's why we observe a progressive shift of the signal, which can be explained like this. However, in the case of mercury cations, we can induce the folding of your DNA. And so, if you look about the signal, we have two kinds of family of curves. And when you plot the position of the resonance according to the concentration, you observe a step like this. And we interpret the step by the beginning of the folding of your DNA. So before the step, you have a strained DNA, and after it, you have the folded DNA. So we are able to say, okay, at this concentration, around nanogram per liter, you have mercury cations. And to confirm these results, we make some circular dichroism measurement. So the idea is to use our solution DNA with mercury cations and consider it as a chiral solution. And the idea of circular dichroism is to shine the solution with a linear polarized light, which can be decomposed into left and right circular polarized lights. And after the passing through the solution, we have a difference of absorption between the two polarizations, which can be interpreted as an elliptical polarization. And the angle of the polarization can give you the circular dichroism of your solution. So here are the formulas, and we observe this. So the dot line is the solution of only DNA. Orange one is a mix between DNA and methylmercury, and we observe any shift of the signal, so we don't have the modification of the morphological aspect of DNA. However, in the case of mercury cations, we have a shift, so we confirm that we have a modification of the shape of DNA. So we focus on this mix, and we change the ratio between DNA and Hg2+, and we observe the evolution of this curve, and when we plot the position of the maximum of this curve according to this ratio, we observe a new step like this. And this curve allows us to say that we need at least 3 Hg2+ per DNA to induce the folding of your DNA. And after it, we have a progressive filling of your fold DNA, which explains the plateau here at the end. So, and all these works were written in my first article at the beginning of the year. So, it's all. Thank you very much.
Long live India and France friendship.